Module 10, Lecture B, Execution and Review. By the end of this lecture, you will be able to implement the full training and evaluation pipeline for the Capstone project using PyTorch 2.10.0. Apply at least one performance or scalability technique, such as torch.compile, AMP, or DDP, to the project. And analyze project outcomes, document lessons learned, and identify areas for future improvement. Running PyTorch experiments. Running the training loop. The training loop is the process where a model actually learns by repeatedly applying the same sequence of steps. For each batch of data, you move the data and model to the correct device, run a forward pass to get predictions, compute the loss against the true labels, and run a backward pass to update the model's parameters. You also set the model to training mode and manage randomness so the process is consistent. This cycle repeats over all batches to form an epoch and is essential for efficient, reliable improvement in tasks like image classification, document summarization, or product recommendation. A strong training loop not only processes data, but also carefully manages state and resources to avoid bugs and performance problems. At the start of each epoch, you switch the model to training mode so layers like dropout and batch normalization behave correctly, and you update any learning rate schedules. For each batch, you clear old gradients, run a forward pass, compute the loss, run the backward pass to get new gradients, and let the optimizer update the model parameters. Throughout this process, you must keep tensors on the correct device, avoid keeping computation graphs longer than needed, and handle exceptions so long experiments, such as training a speech recognition model, do not crash. As your projects grow more complex, the training loop becomes a place to add advanced features that make experiments more efficient and reliable. You can include techniques like gradient clipping for stability, or gradient accumulation to simulate larger batch sizes when memory is limited. Adding logging for statistics such as loss averages or gradient norms helps you detect problems early. A well-structured loop also makes it easier to pause training, adjust hyperparameters, or switch datasets, turning it into a flexible control center rather than a simple script. Python code running the training loop. This material introduces a simple training loop in PyTorch, highlighting how epochs and batches are run in a clear, structured way. It is designed to help you see the overall flow of training rather than every implementation detail. By following it, you can understand what happens at each training step and how the process is organized over multiple passes through the data. The commented line is a reminder to install PyTorch along with its related libraries, TorVision and Torch Audio, using a special index for CPU-only versions. This setup step ensures that all required packages are available to run the training loop on a machine that does not have a graphics processing unit. The line is not meant to be executed as part of the script itself, but instead serves as guidance for preparing the environment beforehand. We begin by importing a few standard libraries that support key tasks in our script. A library for operating system access lets us work with files and directories. A random number library allows us to generate random values, which is important for things like setting seeds so results can be reproduced. A math library provides useful mathematical functions and constants for any calculations needed during training. We start by importing the main PyTorch library, which gives us the core tools for building and training neural networks. Then we import the neural network module, which provides the classes and functions needed to define network layers. Finally, we bring in the optimizer module, which offers optimization algorithms that update the model's parameters during training. Together, these imports set up the essential components for creating and training neural network models in PyTorch. We begin by using the datasets and transforms tools from the Torch Vision library to work with image data. The Datasets tool gives us access to standard image datasets such as MNIST, which we will use for training. The Transforms tool lets us define operations like converting images into tensors and normalizing them. These transformations are essential to properly prepare the images before they are passed into a neural network. We set a fixed seed value of 42 so that any random operations in our code give the same results every time it runs, which is essential for reproducibility. We first applied this seed to Python's built-in random number generator, and then to PyTorch's random number generator using its manual seed function. Using the same seed across these systems makes results consistent between runs, which is especially important for debugging and for fairly comparing different experiments. This code chooses which device to use for the training loop by first checking whether a CUDA-capable graphics processor is available. If such a GPU is found, it runs training on the GPU. If not, it falls back to the CPU. This approach ensures the training process automatically uses the most powerful hardware available for better performance. This line reports the version of PyTorch in use and the hardware device selected for training, which may be a graphics processor or a central processor. Knowing this helps you confirm that your environment is set up correctly. It also lets you verify that your code is running on the intended hardware, which can influence both performance and compatibility. For the MNIST dataset, we define a transformation that prepares the images for use in PyTorch. The images are first converted into tensors, which are the main data structure used by the library. These tensors are then normalized so their pixel values have a mean of about 0.13 and a standard deviation of about 0.31. This normalization keeps the input data on a consistent scale, which helps make training more stable and efficient. We use the Datasets module from TorVision to download the MNIST training data, which is a standard collection of handwritten digit images for training image processing models. We specify a local data directory and request the training split of the dataset, allowing it to be downloaded automatically if it is not already present. A predefined transform is applied to each image to convert it into a tensor and normalize its values, so the data is in a suitable format for training a model. To speed up training, we work with a smaller subset of the full dataset. We choose a subset size of 512, which sets how many samples we will use. We then select indices from 0 up to this number to identify the specific data points. Using these indices, we create a reduced training set that is easier to handle and allows for quicker experimentation and iteration. We use PyTorch's data utilities to create a data loader for our training set, which is a subset of the MNIST dataset. The loader is configured with a batch size of 64, so each training step processes 64 samples at a time. We also enable shuffling so the data is randomly reordered at the start of each epoch. This randomization helps reduce overfitting by preventing the model from relying on a fixed data order. This section describes a simple neural network class called SimpleMLP, which is a basic multi-layer perceptron built using PyTorch. In its setup, it first flattens each input image from a two-dimensional grid into a one-dimensional vector. That vector, with size 28 by 28, is passed through a fully connected layer that produces 128 hidden units, followed by a ReLU activation to add nonlinearity. A final fully connected layer then maps these 128 units to 10 outputs, representing the 10 possible digit classes in the MNIST dataset. The forward method describes how data flows through the neural network. It first flattens the input into a one-dimensional array so it can be processed by the first fully connected layer. The data then passes through this linear layer followed by a ReLU activation function that introduces nonlinearity and helps the model learn complex patterns. Finally, the output of the activation is sent through a second linear layer, which produces the final predictions, completing the forward pass of the network. We begin by creating an instance of a simple multi-layer perceptron model called Simple NLP. After that, we move this model to the chosen computing device, which can be either a graphics processor or a central processor, depending on what is available. Doing this ensures that all training computations run on that device, improving performance and matching the model to the hardware. We use cross-entropy loss as our loss function because it is well suited for classification tasks where the model outputs class probabilities, and it tells us how closely those predictions match the true labels. To train the model, we apply stochastic gradient descent as the optimizer, which updates the model's parameters to reduce this loss over time. We choose a learning rate of 0.1 to control how large each update step is during optimization. We first check whether the PyTorch library supports a feature called compile, which is used to optimize models. If this feature is available, we apply it to our model. Using compile can make the model run more efficiently on the hardware. As a result, the training process can be faster and overall performance can improve. We define a function that runs one full training epoch. At the start of this function, we switch the model into training mode so that training-specific features, such as dropout, are active. We then set a running loss variable to 0 so we can accumulate the loss over all batches. We also start a batch counter at 0, which lets us track how many batches have been processed. With these values, we can compute the average loss for the entire epoch once all batches are done. The code processes the data loader one batch at a time. For each batch, it takes the features as inputs and the labels as targets. It then transfers both inputs and targets to the chosen computing device, such as a CPU or GPU. This ensures that all calculations run on the appropriate hardware for better efficiency. The code first confirms that the input data has 4 dimensions, which is the usual format for batches of images with batch size, channels, height, and width. It then checks that the target labels are one-dimensional, as expected for a list of class labels for each image in the batch. These checks verify that the data shapes match the expected format and help catch structural errors early, before any further processing is done. Here we reset all model parameter gradients to 0 before computing new ones. In PyTorch, gradients accumulate by default. So if we did not clear them, values from previous batches would mix with the current batch. This would distort the gradient calculation and lead to incorrect parameter updates during optimization. By zeroing the gradients, each batch starts with a clean slate, and the optimizer updates the model based only on the current batch's data. The code runs a forward pass through the model, meaning it feeds the input data through all layers of the neural network to produce predictions. These predictions are then used to compute the loss by comparing them with the actual target values. This loss value is essential because it guides how the model's parameters are updated during training. The code verifies that the number of model predictions matches the number of target labels. This check ensures that every input in the batch has a corresponding output from the model. By doing this, it maintains consistency between what the model produces and the expected answers. This consistency is essential for correctly evaluating and training the model. In this step, we compute the loss for the current batch using the cross-entropy loss function, which is commonly used for classification problems. This function compares the model's predicted outputs with the true labels and measures how well they match. It produces a single numerical value that represents the error for the entire batch. This loss value is then used during backpropagation to adjust the model's parameters and improve its performance. This step in the training loop runs the backward pass, which computes how the loss changes with respect to each model parameter. These values are called gradients. They are crucial because the optimizer uses them to update the parameters. By repeatedly updating parameters based on these gradients, the model gradually learns from the data. The optimizer step function updates the model's parameters using the computed gradients. This update is a key part of the training loop because it changes the model's weights to reduce the loss function. By repeatedly applying this step, the model gradually improves its performance on the given task. The code adds the loss from the current batch to a running total so that the average loss can be computed later. It first converts the loss to a simple numeric value using a method that extracts its scalar value. Then it increases the count of process batches by 1. Together, these steps track both the total loss and how many batches have been seen during the epoch. At the end of each epoch, the code computes the average loss by dividing the total loss accumulated across all batches by the number of batches processed. This step normalizes the loss over the entire epoch, so it becomes a consistent and meaningful measure of model performance. The function then returns this average loss value, which can be used to track training progress and decide when to adjust the training process if needed. We set the number of training epochs to 3, meaning the model will pass through the entire dataset 3 times. This is intentionally a small number, so the training remains quick and easy to manage. It is chosen mainly for demonstration, rather than for achieving the best possible performance. The code runs a loop over a set number of training epochs, meaning it makes several complete passes through the dataset. In each pass, it calls a training function that handles all the steps needed to train the model for that epoch. This function receives the model, data loader, optimizer, loss function, and device, and then performs the training logic. After each epoch, it returns the average loss, which is used to track how the training is progressing over time. For each training epoch, we print a brief summary showing the epoch number and the average training loss, rounded to 4 decimal places. This summary gives a quick snapshot of how the model is learning over time. By watching how the loss changes across epochs, we can track improvements and spot potential problems during training. The final line of the script prints a message confirming that the training loop finished successfully. It indicates that the entire process ran from beginning to end without errors. This message reassures you that the code executed as expected and the training completed smoothly. This script shows a simple PyTorch training loop for a basic neural network on a small portion of the MNIST handwritten digit dataset. It sets a fixed random seed for reproducibility, checks for a GPU, and defines a multi-layer perceptron with one hidden layer for digit classification. The data is normalized and loaded in mini batches, and the model is trained for 3 epochs using stochastic gradient descent with standard forward and backward passes. After each epoch, the script prints the average training loss to track learning progress, and it ends by confirming that the training loop finished without errors. Experiment, metrics, logging. To move from simply running a model to building one that can be trusted and improved, you need systematic logging of experiment metrics. Instead of just printing results to the console, consistently record key measures like loss, accuracy, and any task-specific scores during both training and evaluation for every epoch. For example, a medical image classifier should track loss along with sensitivity and specificity to show whether it is truly learning. Integrating this kind of metrics logging into your pipeline creates a clear history of how the model evolves, which is essential for explaining design choices and reproducing results later. Effective metrics logging has 3 main parts: immediate feedback during training, structured storage, and clear visualization. Instant updates on metrics like epoch progress and averages help you detect problems early. Storing metrics in a consistent format, such as CSV files or databases with clear run and parameter names, makes later analysis easier. Visualization then turns these stored metrics into plots that reveal how choices like learning rate affect performance, such as balancing validation loss and hit rate in a recommendation system to manage both accuracy and cost. When logging model performance, go beyond basic accuracy and loss so your metrics reflect real application goals. For example, a fraud detection system should track precision, recall, threshold behavior, and how many transactions are flagged, while a language model might monitor perplexity and response length over time. It is also important to record contextual details such as random seeds, model versions, and pre-processing steps to make experiments reproducible. Together, rich metrics and thorough metadata turn your training pipeline into a stronger framework that guides future model improvements. Python code, experiment metrics logging. This material introduces a simple example of logging experiment metrics during model training. It uses TensorFlow to simulate a training process and focuses on how to record key performance measures over time. The main goal is to track these metrics so you can monitor and visualize learning progress throughout the experiment. By the end, you should understand how basic metric logging supports analyzing and improving training behavior. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this specific version makes sure the code runs with the expected features and behavior. Specifying the version helps avoid problems that can occur when a library is updated or changed. This practice improves consistency and compatibility when running the code. We start by importing a few key Python modules for our work. The operating system module lets us interact with the file system. The random module allows us to generate random numbers, which is useful for tasks like shuffling data. We then import NumPy for efficient numerical computations with arrays. Finally, we bring in Matplotlib's plotting tools so we can create visualizations of our data and results. We begin by importing TensorFlow, a major library used for machine learning and deep learning. This gives us access to its tools for building and training neural networks. After importing, we check the TensorFlow version to confirm it matches what our project expects. Knowing the exact version helps avoid compatibility problems and unexpected behavior caused by differences between releases. We set a fixed seed value, such as 42, so that any random numbers generated are the same every time we run the code. This involves setting the seed for Python's built-in random number generator, then for NumPy's random number generator, and finally for TensorFlow's random number generator. Doing this makes all random behavior, including things like initializing neural network weights, deterministic. This consistency is important for debugging and for reliably comparing results across different runs. The code first asks TensorFlow which physical devices are available and specifically checks for any graphics processing units. Based on this, it sets an internal choice to use either the graphics processor if one is found or the central processor if not. This selection is mainly used for logging or information, so the user knows whether computations will run on a GPU or on the CPU. The code first prints the TensorFlow version being used so you can confirm compatibility and understand the environment. It then checks whether a GPU is available by listing physical devices of type GPU. If a GPU is found, it selects the GPU as the computing device. Otherwise, it falls back to the CPU. Finally, it prints both the TensorFlow version and the chosen device, summarizing the computational resources available for the experiment. This step loads a subset of the MNIST handwritten digits dataset using TensorFlow's Keras tools, and splits it into training and testing parts. The images and their labels are separated into training data and labels, and testing data and labels. This dataset is widely used to train and evaluate machine learning models for image classification. Using separate training and testing sets lets us train the model on one portion of the data and then measure how well it performs on new, unseen examples. To keep the dataset small and the training time short, we limit the training set to 2,000 samples and the test set to 500 samples. We then take only the first 2,000 entries from the training data and adjust the training labels to match this reduced set. This controlled reduction speeds up model training while still providing enough examples for the model to learn useful patterns. To speed up evaluation, we use only a limited portion of the test data instead of the entire dataset. We do this by selecting the first 500 test images and their matching labels. This smaller subset is enough to assess performance while greatly reducing the time and resources needed for testing. The code converts the training and test images to floating point numbers and scales all pixel values to lie between 0 and 1 by dividing by 255, the maximum value in an 8-bit image. This process, called normalization, puts all inputs on a consistent scale. Doing this helps the neural network train more effectively and improves its stability and performance. Before using convolutional layers, we must add a channel dimension to the training and test image data. We do this by expanding the data arrays so that each image changes from a two-dimensional shape to a three-dimensional one. In this new shape, the added third dimension represents the single color channel. This step is essential because convolutional neural network layers require input data to include a channel dimension, even for grayscale images such as those in the MNIST dataset. Before building the model, the code checks that the number of training samples matches the expected amount, confirming the data was sliced correctly. It does the same for the test samples to ensure the test set has been reduced as intended. These checks act as early safeguards, catching any mismatches in data size before model training begins and helping prevent later errors. We build a small convolutional neural network using a sequential model. It starts with a two-dimensional convolutional layer with 8 3x3 filters and a ReLU activation, taking 28 by 28 grayscale images as input. This is followed by a 2x2 max pooling layer to reduce the spatial size of the feature maps. The result is then flattened into a one-dimensional vector and passed to a dense layer with 32 units and ReLU activation. Finally, an output dense layer with 10 units and a softmax activation produces a probability distribution over the 10 MNIST classes. The model is now being compiled, meaning it is prepared for training. An atom optimizer with a small learning rate is chosen to update the model's weights and reduce the loss. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification with integer labels. In addition, accuracy is selected as a metric, so we can monitor how often the model predicts the correct class during training and evaluation. We create a dictionary to record key metrics during training, with each metric stored as a list that grows over time. It includes the epoch number, the training loss, and the training accuracy for each epoch. It also stores the validation loss and validation accuracy. This structure lets us easily collect, organize, and later review how the model performs on both training and validation data throughout the training process. We create a custom callback class called SimpleMetricsLogger by inheriting from TensorFlow's callback base class so we can extend its behavior. In the initialization step, This class receives a log dictionary that will hold metrics collected during training. We call the parent class initializer to set up everything correctly. Then store the provided dictionary in an instance variable so it can be used later while the model trains. At the end of each training epoch, the method makes sure there is a log dictionary and then records the current epoch number. It reads the training loss and training accuracy from the logs, converts them to floating point numbers, and appends them to their respective lists. It does the same for the validation loss and validation accuracy, again storing them as floats. This way, all key metrics are consistently tracked for every epoch, allowing the model's performance over time to be monitored. We create an instance of the custom callback class called Simple Metrics Logger and pass it a dictionary used to store metrics. This callback runs during model training and records values such as loss and accuracy at the end of each epoch. By using it, we automatically capture key training metrics. This log data can then be used later for analysis and visualization of the model's performance over time. The model is trained using the Keras fit method, which takes images and their labels as input and runs for 5 epochs, so the model sees the entire dataset 5 times. It uses a batch size of 64, meaning it updates its weights after processing 64 samples at a time. Separate validation data, made of test images and labels, is used to check performance on unseen examples after each epoch. Training progress messages are turned off to keep the console output clean, and a custom logger callback records metrics such as loss and accuracy at the end of each epoch for later analysis and visualization. We first convert the list of epochs from the metrics log into a NumPy array of integers so we can handle and analyze the epoch data efficiently. Then we convert the list of training losses into a NumPy array of floating point numbers. Putting both epochs and losses into these numeric arrays ensures the data is consistent, easy to process, and ready for numerical analysis or plotting. The code first prints the list of epochs that were logged, giving a quick sense of how many training cycles were completed. It then prints the training loss for each epoch, rounding the values to 3 decimal places for easier reading. This concise output provides a clear summary of how the model's performance changed over the course of training. We create a new plotting area and draw 2 lines showing how accuracy changes over training epochs. One line represents training accuracy, and the other represents validation accuracy, so we can visually compare model performance on both sets. The horizontal axis shows the epoch number, and the vertical axis shows accuracy, with a title describing that this is an example of logging experiment metrics. A legend is added to distinguish the 2 lines. The layout is adjusted so all elements fit neatly, and then the plot is displayed. This script shows how to log experiment metrics while training a TensorFlow model. It sets a reproducible environment, loads and normalizes a small MNIST subset, and builds a simple convolutional neural network compiled with an atom optimizer and sparse categorical cross-entropy loss. A custom callback records training and validation loss and accuracy at the end of each epoch, storing these values in a dictionary while the model trains quietly for 5 epochs. After training, the script prints a brief summary of the recorded metrics and plots training and validation accuracy over time to visualize how the model's performance evolves. This setup provides a straightforward way to monitor and analyze model behavior during training. Managing checkpoints. Checkpointing is essential for reliable deep learning experiments because it lets you pause and resume training without losing progress. A checkpoint stores the model's parameters, the optimizer state, and key training metrics, protecting your work from interruptions such as hardware failures. It also supports experimentation by allowing you to branch from intermediate training states or fine-tune the model on new datasets. In this way, checkpointing serves both as a safety mechanism and as a tool for systematically exploring model behavior over time. When designing a checkpointing strategy, you must decide what to save, when to save it, and how to organize it so it is easy to use later. Regularly store model weights and optimizer state, and keep a separate checkpoint for the best model according to a validation metric, such as validation accuracy in an image classification task. Because metrics can be noisy, also save periodic checkpoints even when the metric does not improve. Include metadata like epoch number, global step, and learning rate in a structured dictionary, and use clear, descriptive file names. This organization makes it easier to compare runs, reproduce results, and deploy models. As experiments and models grow larger, careful checkpoint management becomes essential for both efficiency and scientific rigor. Because large models produce a lot of checkpoint data, it is helpful to keep only recent and best-performing checkpoints, so you save storage while still preserving useful recovery points. In distributed training, make sure that only one process writes checkpoints and that you use a reliable file system to avoid errors. Always test the restore process by loading a checkpoint and confirming that the system runs correctly. This disciplined approach helps maintain a smooth workflow and prevents having to restart training from the beginning. Python code: managing checkpoints. This material introduces a simple example of how to save and load PyTorch models using checkpoints. It emphasizes doing this in a safe and reliable way so your work is not lost. You can treat this script as a basic template and adapt it when running your own experiments. The line that begins with an exclamation mark is a command used in environments like Jupyter Notebooks to install the PyTorch and Torch Vision libraries. PyTorch is a widely used deep learning library, and Torch Vision adds tools for computer vision, such as datasets, model architectures, and image transformations. Running this command makes sure these libraries are installed and ready, so the rest of the script can build and train neural networks using PyTorch. We start by importing 3 standard Python libraries that support our script. The operating system library lets us work with the system environment, such as files and directories. The random library provides tools for generating random numbers and making random choices, which is useful for creating or controlling random behavior. The math library offers common mathematical functions and constants that we can use for calculations throughout the program. We begin by importing PyTorch, which we use to build and train neural networks. We then import the neural network tools from PyTorch, so we can define layers and model architectures. Finally, we bring in the optimizer tools, which provide algorithms to update model parameters during training. Together, these imports create the basic setup needed to efficiently build and train a neural network model. We set a fixed random seed so that any operations involving randomness give the same results every time the code runs. This is important for making experiments reproducible. By initializing the random number generator with a specific value, such as 42, we lock it into a known starting state. As a result, each call to a random function will produce the same sequence of values across runs, allowing us to reliably repeat and compare results. We start by setting a random seed in PyTorch so that any random operations produce the same results each time we run an experiment, which is important for reproducibility. We then check whether a CUDA-compatible GPU is available. If it is, we also set the random seed for all CUDA devices. This makes sure that computations on both the CPU and GPU are consistent and repeatable across different runs. This code chooses which computing device to use by checking if a GPU with CUDA support is available through PyTorch. If CUDA is detected, it sets the device to the GPU. If not, it falls back to the CPU. This approach lets the program automatically take advantage of faster GPU acceleration when possible, which can significantly improve performance in deep learning tasks. This line displays the version of the PyTorch library you are using and the computing device selected for running operations. It helps you confirm that the intended PyTorch version is installed. It also tells you whether your code will run on a graphics processor or on the main processor, which can influence both performance and compatibility. TinyNet is a small neural network built by extending PyTorch's base neural network module. In its initialization, it first calls the parent initializer, then defines a simple sequence of layers. The network uses a linear layer to map the input dimension to a hidden dimension, applies a ReLU activation for nonlinearity, and then uses a second linear layer to map the hidden dimension to the number of output classes. This sequence fully specifies the model's architecture. The forward method describes how data flows through a neural network. It receives an input tensor and sends it through the network sequence of linear and activation layers. By calling this sequential model, the input is transformed step by step. The result is an output tensor that can then be used for further processing or for computing the loss. This function builds a small synthetic dataset for classification. It first generates a tensor of random feature values drawn from a normal distribution, using the requested number of samples and input dimensions. It then creates random integer class labels for each sample, ranging from 0 up to 1 less than the total number of classes. Finally, it returns both the features and the labels together, ready to use for training or testing a model. This function runs one training step for a single epoch. It first switches the model into training mode and clears any existing gradients in the optimizer. The model then processes the input data to produce output logits, which are compared with the true labels using a loss function. This loss is backpropagated to compute gradients for all model parameters, and the optimizer updates these parameters to reduce the loss. Finally, the function returns the numeric loss value so it can be used to monitor training progress. The function evaluates a trained model by first switching it to evaluation mode and disabling gradient tracking to save computation. It feeds the input data through the model to obtain logits, then compares these raw predictions with the true labels to compute the loss, which measures prediction error. It then selects the class with the highest logit for each input as the predicted label, and counts how many of these match the true labels. The accuracy is found by dividing the number of correct predictions by the total number of samples, with a safeguard to avoid dividing by 0. Finally, the function returns the loss as a numeric value and the accuracy as a proportion of correct predictions. This function builds a checkpoint dictionary that captures the current state of a training run. It records the current epoch number, the model's internal state, the optimizer's state, the best validation loss seen so far, and the configuration settings. By returning this dictionary, the function provides all the information needed to save, resume, or later analyze the training process from that specific point. To safely save a model checkpoint, we first make sure the target directory exists so saving does not fail. We then choose a path for the main checkpoint file, often called last checkpoint, and store the current model state there using the PyTorch save function. If this checkpoint represents the best performance so far, we also choose a separate path for a best checkpoint file and save the same state there. This way, we always keep both the most recent model and the best performing model available on disk. This function attempts to load a saved training checkpoint from a given directory. If no checkpoint file is found, it returns default values indicating that training should start from the beginning and that no best validation loss is recorded. If the file exists, it loads the checkpoint data onto the CPU, restores the model's parameters and the optimizer state from the saved information, and then returns the next epoch number to continue training from, along with the best validation loss stored in the checkpoint. In the main function, we begin by creating a configuration dictionary that defines the key settings for our experiment. It sets the input feature size to 8 and the hidden layer size in the neural network to 16. The model is designed to classify inputs into 3 output classes. We train for 4 epochs with a learning rate of 0.01, which controls how quickly the model updates its weights. The configuration also specifies a directory named checkpoints demo, where model states are saved during training. We begin by creating a small synthetic dataset to train and test our model. Using a normal distribution, we generate random input features for 64 training samples, with the input dimension and number of classes determined by the configuration. We then build a validation dataset of 32 samples using the same settings. Together, these datasets let us simulate a controlled classification task for training and validating the model. Before the training loop begins, the code checks that the number of features in the training data matches the input dimension defined in the configuration. It performs the same check on the validation data to ensure consistency. These assertions confirm that all data has the correct shape and help detect mismatches early. By catching such issues before training and evaluation, they prevent errors and make the training process more reliable. We begin by moving the training features to the chosen device, such as a GPU or CPU, so computations run on the most efficient hardware. We then place the training labels on the same device to keep the data consistent. Next, we transfer the validation features to this device to prepare them for evaluation. Finally, we move the validation labels as well, so all training and validation data are ready to be processed on the selected hardware. We begin by creating a TinyNet model, a simple feed-forward neural network whose input size, hidden layer size, and number of output classes are taken from a configuration. The model is then moved to the chosen computing device, such as a graphics processor, to speed up calculations. We set the loss function to cross-entropy loss, which is appropriate for classification because it compares predicted class probabilities with the true labels. Finally, we create a stochastic gradient descent optimizer using the learning rate from the configuration, so the model's parameters can be updated during training at the desired pace. The code is set up to resume training from a saved checkpoint instead of starting over. It calls a loading function that restores the model and optimizer from the checkpoint directory if one exists. This function also returns the epoch to restart from and the best validation loss achieved so far. Using this information, training can continue from the previous point, preserving progress and the best model state. We print a message that shows the starting epoch and the best validation loss so far, to make it clear where training is resuming and how well the model has performed up to that point. This information helps us track progress and compare future results after resuming training. The starting epoch is shown as a whole number, and the best validation loss is rounded to 4 decimal places to keep the output easy to read and interpret. We run a training loop over the configured number of epochs, and in each epoch, we train the model on the training data to update its parameters. After training for that epoch, we evaluate the model on the validation set to compute validation loss and accuracy. We compare the current validation loss with the best one seen so far, and if it is lower, we update the best value. We then create a checkpoint that stores the current epoch, the model and optimizer states, the best validation loss, and the configuration, and save it to disk, marking it as the best checkpoint when appropriate. Finally, we print a brief summary of the epoch's training loss, and validation accuracy to monitor progress over time. This script shows a basic example of checkpointing in PyTorch. It builds and trains a small feed-forward neural network on a synthetic classification dataset, using a fixed random seed and choosing a device based on whether a GPU is available. During training, it tracks validation loss each epoch, saving the best performing model as the best checkpoint, and always saving the most recent model as the last checkpoint. When the script starts, it tries to load any existing checkpoints so training can resume from where it left off. After training, it evaluates the best saved model on the validation set and reports loss, accuracy, and progress over epochs, making it easier to recover and use the best model even if training is interrupted. Performance optimizations in PyTorch. Adding torch.compile. When you add compilation to your training pipeline, the framework analyzes your model and operations to build a more efficient execution plan. Instead of running each operation one by one, it traces and optimizes the whole computation graph so it can execute faster on modern hardware. This lets you keep your model definition, data loading, and training loop the same, while still gaining optimizations such as combining multiple operations into a single kernel. As a result, you can significantly improve performance on a single GPU or CPU without rewriting your codebase. To integrate compilation into your project, build your model as you normally would, then pass it through the compilation interface, and use the compiled version in place of the original. You keep the rest of your training and evaluation code the same, which makes it easy to adopt compilation gradually. Start with a configuration that focuses on correctness and compatibility. Confirm that training behaves as expected, then measure any speed improvements. Once training is stable, you can experiment with more aggressive compilation settings to further optimize performance. When you add compilation to your project, expect an initial warm-up phase while the system optimizes the computation graph, followed by much faster runs that are especially helpful for long training sessions. However, highly dynamic model behavior, such as frequent changes in control flow, can reduce the benefits of compilation and may require you to adjust your model. In a Capstone project, this might mean making the architecture more stable or moving more logic into tensor operations so it can be better optimized. By thoughtfully integrating compilation and monitoring its impact, you can turn a prototype into a more efficient system that is better suited for real-world deployment. This script shows how using the compile feature in PyTorch can speed up model training. It builds a small feed-forward neural network called TinyNet and trains it on a synthetic classification dataset made of random features and labels. The script runs training twice, once in the usual eager execution mode and once in compiled mode, measuring the time and final loss for each run. In most cases, the compiled version trains faster than the eager version, especially on CUDA-enabled hardware, demonstrating the performance benefits of using compile for compatible models. Using AMP or DDP. When training models on large datasets or complex architectures, automatic mixed precision, or AMP, is a key technique for improving efficiency. AMP speeds up GPU computation by using lower precision where it is safe, while keeping higher precision for numerically sensitive operations. This reduces memory usage and increases throughput, allowing faster training or larger models on the same hardware. For example, A medical image segmentation team can use AMP to process higher resolution scans without needing additional memory or new hardware. Distributed Data Parallel Training, or DDP, is a way to speed up model training by using multiple GPUs or machines at the same time. Instead of one device processing all the data in sequence, DDP copies the model to several devices, splits the data across them, and then synchronizes their updates. This parallel processing can turn very long training runs into much shorter ones, allowing you to run several experiments in a single day. As a result, the main benefit is not only faster training, but also the ability to explore more model designs and strategies within tight time limits. When choosing between automatic mixed precision and distributed data parallel training, focus on what limits your project most. If GPU memory is tight or single GPU training is slow, automatic mixed precision is an easy way to speed things up with few code changes. If the model fits comfortably on one GPU, but training is slow because of large datasets or many epochs, distributed data parallel training is usually better because it spreads work across multiple devices. In practice, many projects combine both methods to get the best efficiency and scalability. Always profile your training runs first so you can see the main bottleneck and select the most effective approach. This script shows how to use automatic mixed precision in PyTorch to train a simple neural network on random data. It sets a fixed seed for reproducibility, chooses a GPU if available, or falls back to the CPU, and defines a small feed-forward model with one hidden layer and a ReLU activation. Random inputs and labels are created and moved to the chosen device. Then the model is trained for a few epochs, using the atom optimizer and cross-entropy loss. Automatic mixed precision is enabled to speed up training by using lower numerical precision where it is safe to do so. After training, the script evaluates the model's accuracy on the same random data and prints the final result, providing a clear, beginner-friendly example of integrating mixed precision into a standard training loop. Evaluating optimization results. After you apply performance or scalability techniques, you should carefully measure their real impact. First, decide what improvement matters most for your project, such as shorter training time, higher throughput, or lower memory use. Then record a baseline using your original training setup and compare all changes against it. This baseline lets you confirm that any optimization truly improves the key metric instead of just feeling faster without measurable benefit. Once you have a baseline, you can fairly evaluate optimizations like compilation, mixed precision, or distributed training by keeping the dataset and model architecture fixed, so any performance change comes from the technique itself. Track metrics such as total training time, average iteration time, GPU memory usage, and validation loss to understand both speed and model quality. If, for example, mixed precision cuts training time by 40% but slightly reduces accuracy, you must decide whether that trade-off is acceptable. In some cases, such as recommendation systems, a small accuracy drop may be worthwhile if it enables more frequent model updates and better user engagement. When judging optimization results, do more than compare performance numbers. Also consider stability, reproducibility, and how they affect real-world use. A speed-up is not worthwhile if it makes training diverge, causes exploding losses, or complicates deployment. Check that training curves remain smooth and that validation metrics are consistent with your baseline. Be aware that methods like distributed training can shorten runtime but add workflow complexity. Use both quantitative metrics and qualitative observations to decide which optimizations to keep or adjust. This script tests how a simple feed-forward neural network performs on a synthetic classification task using PyTorch. It runs the same small model twice, once with standard training and once with an optimized version that uses automatic mixed precision when a CUDA device is available. The data has 20 input features and 3 output classes, and the model is trained for a few epochs on separate training and validation sets. For both runs, the script records training time and validation accuracy, then reports the speedup and any change in accuracy. The printed results show the device used and help illustrate the potential performance benefits of mixed precision training on compatible hardware. Reflect, review, improve. Capstone Results Summary. As you finish your capstone, create a clear narrative of your results instead of just listing accuracy or loss values. Explain what your model was built to do, who it serves, and the conditions under which you tested it. Describe your main performance metrics, such as classification accuracy or precision, and always interpret these numbers by comparing them to a baseline and the difficulty and characteristics of the task and data. Your goal is to tell a concise story of your project so that someone unfamiliar with it can understand its impact and its limitations. When summarizing your model's results, do more than report overall scores. Explain how performance varies across different data segments. Check whether the model behaves consistently for the key subgroups or conditions in your application, such as different image qualities or writing styles. Emphasizing these patterns shows you have considered fairness and robustness. Also mention any surprising outcomes, like a simpler model outperforming a more complex one, because these insights can guide future improvements. In your capstone results summary, connect your quantitative metrics with qualitative insights to show how your findings matter in real-world applications. Evaluate whether the model is accurate and stable enough for full deployment, or better suited as a decision support tool that still needs human oversight. Briefly address operational factors such as training time, memory use, and inference speed, and explain how these influence deployment in different environments, including mobile or low connectivity settings. Conclude by emphasizing the main strengths of your solution, its key limitations, and realistic directions for improvement, so your results become a focused analysis that can guide future work. Common PyTorch pitfalls. When reviewing a PyTorch project, pay close attention to how you handle training and evaluation modes, as well as gradient tracking. Forgetting to switch from training to evaluation can distort validation results, especially when using dropout or batch normalization. Similarly, failing to turn off gradient tracking during evaluation wastes resources, while detaching tensors too early can break the computational graph. Reflect on whether you consistently use the correct modes and gradient settings, and consider whether odd metric behavior might be caused by these subtle state and gradient management issues. In many projects, data handling and device placement can quietly limit performance, leaving GPUs underused while CPUs struggle with batch processing. This often comes from inefficient preprocessing, poor batch size choices, slow data augmentation, or mixing CPU and GPU tensors in the same operations, which can trigger costly device transfers and runtime errors. These problems are especially harmful when training models on large datasets, making runs unstable and frustrating. Reflect on your own project to find where data bottlenecks or device mismatches appeared, and think about how a better designed data pipeline could improve both reliability and speed. When evaluating models, you must avoid using training data in your evaluation or repeatedly tuning on the same validation set, because both will give you overly optimistic metrics. Control randomness with fixed seeds and carefully record any changes to training settings so your results are reproducible. In real applications, such as recommendation systems or medical imaging, these mistakes can lead to misleading performance claims. Always check that your data splits are clean, your configurations are tracked, and you have not overfitted to the validation set, so your experiments remain rigorous and your PyTorch workflows are trustworthy. This script illustrates common PyTorch pitfalls related to training and evaluation modes, device placement, and gradient tracking. It uses a simple neural network with dropout on a small MNIST subset, trains it briefly, then compares evaluation while still in training mode versus correctly switching to evaluation mode with gradients turned off. The resulting accuracy difference shows how dropout can harm evaluation if the model is not in the proper mode. The script also verifies that tensors are moved to the same device before operations, avoiding device mismatch errors, and confirms successful computation once everything is correctly placed. Next steps with PyTorch. After completing your Capstone, treat your PyTorch project as an ongoing, evolving effort rather than a finished product. Continue refining your model, data pipeline, and evaluation process, and look for concrete ways to scale and improve them. Focus on growth areas such as handling larger datasets or integrating your model into real applications. For example, if you built a medical image classifier, work on making it reliable across different hospitals. This mindset deepens your PyTorch skills while keeping your work relevant to real-world needs. To deepen your PyTorch skills, focus on areas you did not fully explore in your Capstone project. You might learn how to deploy models efficiently on cloud or mobile platforms, or study advanced training methods like curriculum learning and domain adaptation. If you worked on time series forecasting, try adding external data, such as weather information, to improve your model. These efforts will strengthen your ability to read documentation, troubleshoot errors, and run targeted experiments to better understand how your PyTorch models behave. Look for ways to connect your ongoing PyTorch projects to real professional or research environments so your learning continues to grow. You might collaborate through shared repositories, contribute to open source work, or test your models in small, real-world deployments. For example, if you built a natural language processing tool, you could apply it to live business data and refine it using user feedback. These experiences expose you to challenges like latency, fairness, and interpretability, and push you to use PyTorch more effectively. By actively seeking such opportunities, your Capstone project becomes the starting point of a longer journey in building and improving machine learning systems. In this lecture, you learned to implement the full training and evaluation pipeline for the Capstone project using PyTorch 2.10.0. Apply at least one performance or scalability technique, such as torch.compile, AMP, or DDP, to the project. And analyze project outcomes, document lessons learned, and identify areas for future improvement. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.